Hello everyone, and welcome to the 7th lecture of the Introduction to Media Engineering course. In this lecture, we're going to continue the color spaces topic that we talked about last time. There was like 3 or 4 more slides remaining. And then we will move to the next part of the course where we start talking about video and animation. So last time in this topic of color spaces, we already covered different ways to represent color. We talked about color spaces like the RGB, the CMYK, the HSL, and HSV. So next we talk about the notion of color channels. So we say here that the R, G, and B components of each pixel, they can actually be stored as separate values. Let me explain what this is. So let's say we have an image. That image is 3 by 3, and let's assume that this pixel is full red, this pixel is full green, and this pixel is full blue. If you're using the normal RGB representation, each pixel, as we said, will have 3 bytes, 1 byte to represent the red component, 1 byte to represent the green, 1 byte to represent blue, right? So there are multiple ways to store this. Either that for every pixel, you're storing like 24 bits, like 3 bytes that are consecutive, like in terms of even of storage, you write first the byte of the red color, followed by the byte, a byte for the red component, a byte for the green component, a byte for the blue component for the first pixel, and then you go to the second pixel, 1 byte for red, 1 byte for green, 1 byte for blue, and so on. This is one way. The other way is to represent that image in the form of 3 different matrices. So you would have one matrix, all of them would be, by the way, would be 3 by 3. So these are the 3 matrices that are all 3 by 3. Okay. And the first one will be representing the red component of all pixels. The second one will represent the green component of all pixels. And the third would represent the blue component of all pixels. So for example, if we take the first pixel in the image, this one, which assuming here it was full red. If it's full red, you should have full value for the red component, 0 for green and 0 for blue. So how are we going to do that? Then this is how we can do it. We can write here in that first location, we write the value 255. Second one would be 0, third one would be 0. Why? Because the second and third pixels, one of them is full green, the other one is full blue, so they don't have red component. When we go to the green, so that first matrix, we call it the red channel. Okay. When we go to the second channel, which is the green channel, in that case, this location would have the value 0. Okay. This one will also be 0, while this one will have 255. Why? Because that pixel, that second pixel in the first row, its color is full green. While for the last pixel, or sorry, the last channel, the blue channel, the value here would be 0, here would be 0 as well, while the last value here would be 255, because we have that pixel is full blue, no green, no red. So now by doing this, it's like you are representing the original image in 3 images. One represents the red color or the red component of each pixel, one that represents the green component of each pixel, and the third one represents the blue component of each pixel. Okay, let's see an example. Looking at this picture here, this is an RGB image, colored image, where every pixel is represented with 24 bits, as we said. Now we're looking here at the red channel, the red component of all pixels. We're looking here at the green channel, and this is the blue channel. So one thing you notice here, if you look at those pieces of cherry, they have a red color, right? Which means that in terms of the red component of those pixels, you should have a high value for red, very low value for green, and very low value for blue, because that pixel is red, right? And this is what we see here. If you look at this, this is the red channel. You can see that the places that represent the cherries, they have very bright value. Why bright? Bright here indicates a high value. So because these pixels, they are all red, so their values would be similar to this, like 255, for example. So if you represent the red channel as a grayscale image, you would expect that for red pixels to have high values. Now look at the green and the blue channels. The green channel, for these pixels, they have very low value, indicating that we don't have green components here and we don't have blue components here. But if you look, for example, at those pieces of the plant where you have green color, you see the green, because it's green, in the green channel, these are bright values. So now, why are we doing this? Because once you represent images in the form of these color channels, there are things that you can do to play with each color channel independently. So the three values can be treated as grayscale images, as we said. They're called channels, and we will see next how we can actually make use of this representation. So let's see an example where the representation form of color channels would be useful. So what we can do is that each channel, whether the red, the green, or the blue, it can be actually manipulated independently. This can be used to make adjustments to the channels which would alter the colors of the image. So as an example, let's look at this image here. This image was taken in the fall season. Okay, that's why this area, although it's supposed to be grass, it has those like orange or reddish color because of the season. Now imagine that you have this image and you would like to create another image that represents the same area but actually in the spring, not in the fall. So how would we do this? Now this is simple. The reason that this looks like this is that most probably the red component of those pixels is high. So if I represent this image in the three color channels, red color channel, green color channel, and blue color channel, I can go and then set the red component of all of these pixels to be 0, so removing any red component, and maybe increase the green components for these pixels. And then this is what you will get. So this is how you can obtain a scene for the same location, but now it's in the spring instead of the fall season. The color balance, the hue, the saturation, color replacement, all of these things can be done once you represent images in the form of color channels. This is another example. For example, if you have an image for this door, this is like a red door. What if you would like to change the color of the door from red to become blue? Well, this is not that hard, because if I look at the red channel of this image, most probably these pixels will be very bright. Now, if you would like to replace the red with blue, then this wouldn't be that hard, because what you will do is that you are going to suppress all the red values, so make all of the red pixels 0, and replace all pixels that are red with blue values. So you can increase the blue component for those pixels and decrease the red component for those pixels, and then you get an image like this one. Looking at this image, you wouldn't actually feel that this image was actually coming from this one. In fact, this image was obtained from this image by just downgrading or reducing the value of the red components and increasing the value of the blue components. So by splitting an image into color channels, these things become very easy. So other than the color channels, the red, green, and blue, we have another sort of a channel which is called the alpha channel. The alpha channels, they can be treated as additional color channels, although they actually do not represent color. The alpha channel is treated as a mask that can isolate an object from a picture. So for example, if you look at this image is an image for a face of someone. And this image here is represented in the form of red, green, and blue channels. Okay, we're just coloring the red with the red color, the green with green, and blue with blue, just for representation. Okay, now what if you would like to extract the face from the image? So what you will do is that you will form what's called an alpha channel. It acts as a mask where the white locations represent pixels that you will take as they are from the color channels, while the black parts represent places that will become transparent. Like, you can use that to create a layer, for example, and put on another image. Now, what you will do is that you will take this is like something binary. The white would be represented with 1, the black would be represented with 0. What you will do is that you will take this and multiply it by the R and the G and the B color channels, element-wise multiplication. So those pixels that will be multiplied by 1, they will be as they are, while the ones that are multiplied by 0 will be removed. And these will be treated as background or actually transparent areas. Okay. Once you do that, you can extract the face, and then you can composite. You take that face and put it on another image, and then you get something like this face on a different background. This is actually used in filmmaking. Okay, so you probably have seen this before when they would be shooting a movie or something, and then you see that the actor is filmed in front of a blue screen or a green screen. They call it the blue screen technique. We say here that if a person is photographed against a blue background and ensuring that none of their clothing is blue, so that person wouldn't wearing anything in blue, an alpha channel can be created for the blue background to isolate the person. So you can imagine that, okay, if we have someone who's doesn't have anything in blue in his clothes, and then that person is filmed in front of a blue screen, then what we can do is that we can make an alpha channel that actually removes the blue color and make it transparent. Once we have this, then we can insert later on by editing any background here instead of the blue screen or the green screen. Okay, the choice of blue or green depends on the clothing of the actors, because if they have to wear something in blue, then the blue screen wouldn't work. They have to go with a green background in that case. So the blue screen technique is commonly used actually in video and filmmaking, and it's used for that purpose. Okay, so this is the end of the color spaces lecture. Now we're going to move to the next topic, which is by now we actually talked about digital still images, and we talked also about color channels and the color spaces. Now we move to the next part of the course, which is video and animation. So the next topic in the course is video and animation. We started first with images because, as we have mentioned before, videos or animation, they are actually created out of frames, and the frames are actually images, like still images. The whole idea of creating a video or animation is just by stacking multiple still images back to back, playing them very quickly, and that would give you the feeling of a video. So this is the whole idea. That's why we started with digital still images, and now we move into video and animation. So video has become an important feature of the internet after the development of digital video technology and higher network speeds. Like right now we can watch video on Facebook, on YouTube. It's now a very important component of all the traffic on the internet, right? Now, how can we? This has been all possible because of the development of what's called digital video, which is representing video in digital form. But before we talk about digital video, let's talk about the analog video. So first of all, how do we capture digital video? You can capture digital video. I'm going to talk later on about the analog video using a digital camcorder that records video on a tape using one of the following formats: the mini DV, DV Cam, or DVC Pro, and then connect that to the computer using what's called the FireWire interface. So there is a possibility that you can record digital video on a tape actually using any of these formats. However, like currently some camcorders, they have an internal hard disk while others write directly to DVDs. So now you're using the digital technology for storage where you can write directly to a hard disk or a DVD. So now you will have your video directly recorded on a digital medium. Okay. Now the DV camcorders or digital video camcorder, or even the videotape recorders connected to computers over Wi-Fi or FireWire, sorry, are used for reasonable quality digital video capture. So this will give you a very good quality in terms of the video. However, cheap video cameras are often built into mobile phones and laptop computers or used as webcams. So these cheaper video cameras, they mostly, because for example, if you're dealing with a mobile phone, the storage is limited. In that case, you have to use some sort of compression. So they use what's called the Mpeg 4 as a compression technique, which we will cover. We'll talk about it in the compression topic later on in the course. And USB 2 for connection. Now, before we go into digital videos, we have to talk about video standards, and mainly we talk about the analog one of them. So the digital video standards, when people started putting them, they inherit features from the analog broadcast TV. So the TV transmission that comes to our TVs, like, it uses some sort of a standard, and the digital video, when it was created, it actually was inheriting features from them. So let's talk first about the standards of the analog broadcast TV. The first one is called the National Television Systems Committee, or the NTSC standard, and this is the one that's used in the US and Japan and South America. So all TV transmission in these countries follow that standard. While in Western Europe, Middle East, and China, including, of course, Middle East, including Egypt, we use what's called the PAL system, or the phase alternating line standard. There is also the sequential couleur avec mémoire, or the SECAM standard. This is the one that's used in France, Eastern Europe, and Russia. So these standards, they differ in a number of things, as we will discuss later on. But here, these things, they represent the regular transmission of TV. We're not talking here about satellite transmission. We're talking here about the analog transmission. You know, like you can have an antenna and then capture TV signal transmitted to you through ground stations. We're not talking about satellite stations. And this is what the NTSC, the PAL, and the SECAM. In fact, the NTSC that's used in the US, like back in the days, if you buy, for example, a TV from the US and you try to use it, for example, in Egypt, it wouldn't actually work. And the reason is because it's actually using the NTSC standard. So it's designed to receive signals according to that standard, so it wouldn't work in a PAL system. Okay. This map here shows the distribution of the countries over these, or the distribution of the standards over these countries. Like the green ones represent the NTSC standard. The blue here represents the PAL system. The orange here represents the SECAM, and this is how the countries are distributed on them. Okay. Okay, so now how do television sets work? So television sets were traditionally based on cathode ray tubes. This is actually before the invention of LCD and LED screens, but it's important actually to discuss the old cathode ray tube devices, because the technology that was used at that time had an impact on the development that happened later on. So what are the cathode ray tubes, or the CRTs? These are those TV, like box TVs, you know, like those TVs that have an extension in the back. They look like this. If you look at a TV, a cathode ray tube, like from the side, cathode ray tube device would probably look like this. Okay, here this is actually the screen, and the back of the TV, inside it has the cathode ray tube. What's the cathode ray tube? It's a tube that produces actually an electron beam that goes and hits the surface of the screen. So what's the function of this? So if we look at the screen actually, if we zoom in on a screen, this is how the screen would look like. If we closely zoom in on it, we talked about this picture before, where every pixel will be actually represented with three particles, or three parts of phosphorus. Okay, so every three, if I draw it here, if this is how the screen looks like, okay, imagine that the screen is divided into pixels. Now each pixel, if I zoom in on one, it will have three lines. One that is red, like if I use color here just to be more accurate, you would have one that is red, and one that is green, and one that is blue. So the idea here is that these three phosphorus lines, or small like parts, when they are actually hit by an electron beam from the back, they glow, they generate light. So this is how an image will be formed. Okay, you have the screen is full of those phosphorus dots. The cathode ray tube would produce that electron beam. This is what happens. The screen, as I said, is divided into horizontal lines, and the electron beam sweeps, or the electron beams that are coming from the CRT, they sweep across the screen, tracing each line and moving down to trace the next. So what happens is, this is the electron beam. It starts with the top part of the screen. It's like hitting here first. Now, the thing is, if let's assume that the first pixel was complete red, it's a red pixel. So in that case, the electron beam, when it, like, let me draw it here in black, the electron beam starts here at the first pixel and it keeps like going horizontally like this. Okay, it's like traversing the image horizontally. Once it finishes the first line, it goes down to the second line, third line, fourth line, and so on. Now, while it's moving from left to right, the electron beam wouldn't be on all the time. It would be on only when you want that pixel to generate light or to have some color. So the electron beam starts from the top left pixel and it sweeps the horizontal line, or the first line horizontally. Now let's assume that the first pixel is supposed to be red. So in that case, the electron beam, when it's hitting the red phosphorus, it will have intensity, like it will be on. That electron beam will be on. So if it's on at the time it actually crosses that red dot, then that red dot will produce light. And then when it goes to the green one, it will be turned off. The blue one will be turned off. So in that case, the mix here, because these dots or these phosphors, they are very close to each other. So now the red one is on, the green is not on, the blue is not on, and that's how you get a red pixel. Now let's assume the next pixel is white. Let's assume this pixel is white. White can be generated by having full red plus full green plus full blue. Now these things are very close to each other. The electron beam, of course, passes through very quickly. You don't even notice it. So if you want this pixel to be white, you need the red, the green, and the blue phosphorus to glow or produce light. Therefore, the electron beam will be on for the three of them, and so on for all of the pixels. Once it finishes the first line, it goes down to the second line, starting from the first pixel in the second line, and then going horizontally, and so on until it finishes the whole screen. This is what's called raster scanning. Okay. So the picture we see is built up from top to bottom as a sequence of horizontal lines. So this is the technology that was used for the CRT screens. You maybe, like, sometimes in the labs you see those computer screens, that the box screens. This is how they work. Now the thing is, you might say, okay, but I don't feel all of that when I'm watching anything on a CRT screen. I don't feel that lines are getting drawn or anything. Yes, why? Because the screen has to be refreshed, or actually gets refreshed in that technology 40 times per second. And why? Because, as you remember before, we talked about diffusion frequency, and we said that for the persistence of vision phenomenon to be present, if we refresh a screen more than 40 times per second, we wouldn't even notice that these are different frames. So what happens is that normally the screen, this drawing of the screen from the top left pixel down to the bottom right pixel, this happens at least 50 or 60 times per second. Now when this is happening very, very quickly at that rate, you wouldn't actually notice that these are different images or that these things are getting drawn in front of you. Okay? So this is what we call the raster scanning principle, and this is how an image is formed on a CRT screen. Now this is important. Why? Because when the technology later on switched to LED and LCD screens, the idea is, like, for example, for LED screens, you will have, instead of having these three phosphorus parts, so you'll have three LEDs, one red, one green, one blue. Now those LEDs can generate light just by connecting current. So you don't need this. So the whole thing is, in LCD or LED screens, they are like flat screens. They are very thin in terms of, why? Because you don't need that CRT or that cathode ray tube in the back anymore, because those LEDs can generate light if they are connected to electricity. So they have a different circuit that actually operates those LEDs to get the screen, but still every pixel is formed out of 3 types of LEDs or 3 colors, red, green and blue, to generate any color. Okay, so this is how the image gets produced in CRT screens. Now when we talk about transmitting an entire picture, you can imagine that transmitting an entire picture which has multiple lines, and many times, because you have, as we said, you have to refresh the screen 40 to 50 or 60 times per second. So for the TV broadcasting, they have to transmit every second at least 50 frames. So transmitting an entire picture many times a second requires large bandwidth. You can imagine that you need a large bandwidth to transmit that amount of data per second. Now, there is a little trick that could be used in order to reduce the amount of transmitted data and might not really affect the quality of the image that much, which is using interlacing. The idea here is that each frame is divided into 2 fields, odd and even lines, and these fields, the odd field and the even field, they are transmitted one after the other and interlaced for display. What do you mean by this? If you look at this image here, we started like this is how the image looks like. This is line number 1, line number 2, line number 3, and so on. So we colored the odd lines in blue or purple here and the even lines in orange. And the idea is that at any time moment, the transmitter that transmits the TV signal wouldn't actually be transmitting both of them. It would transmit only either the odd, and then the next time point transmits the even. Odd and then even, odd and then even. So if you think about it, it's like the total amount of data that's being transmitted is half than if you are actually transmitting the whole frame. And the good thing is, by receiving only 1/2 of the frame at any time moment, so the persistence of vision will help not noticing that at any moment only half the image is displayed. So you receive, like, let's say the odd field, the odd lines, you display them, while the even lines could be actually blank, nothing is there. And then, right after a very, very short amount of time, remember that this is sent like 50 times per second. So the time between 2 frames, if you think about it, we have 50 frames per second. So 1/50 of the second, this is the interval between 2 frames. Okay, so which is actually, this would be 1/5 is 200 milliseconds. This is like 20 milliseconds. So every 20 milliseconds you get a new frame. This is a very, very short amount of time, you wouldn't even feel it. So the first time point, we're displaying the odd field, like the odd lines only, and then 20 milliseconds later, we are displaying the even, we are receiving the even lines and displaying them. And keep doing this, odd, even, odd, even. Now, because of the persistence of vision, you wouldn't actually notice, because this is happening very quickly in your brain. This would be like as if it's one image that's being displayed. So using that idea, we are transmitting half the amount of data and still not compromising the quality that much, because we wouldn't actually notice it. So this is what's called interlaced display. And actually, a number of years ago, there were like even LED and LCD screens that are by design interlaced. They can deal with interlaced data, and they display only half the frame at any time moment. Okay. Now, one problem with the interlaced frames is that a little error can happen when they are displayed progressively or exported as still images. And this error is called combing. So let's see what happens. Let's assume we have an image, like this is like part of the clothes of someone, and this is the odd field, okay, and this is the even field, okay. So these are only the odd lines in the image, and these are the even lines in the image. Now, if this part is actually moving very quickly, so assume that there is a movement in between these 2 fields, and that movement is very quick. So when these 2 frames are mixed together, you get what you can see here. Like some lines belong to this image, and some other lines assume that this thing moved to the right, so some other lines will belong to that image. So you see, like, there is what's called like combing. Like you can see it even here. When the even and the odd fields are mixed together, when they are displayed progressively, this is what happens. So that is one of the issues, that if you take a video that is being actually transmitted in an interlaced way and try to export it as a still image or displayed progressively, you might get this combing effect. Okay. So the rate that was actually chosen to transmit frames, whether it depends of course on the standard in the country, but it was actually chosen to match the local AC line frequency. You know, like in Egypt here, the frequency of the alternating current, the one that we get from the electricity plugs, is 50 Hertz, right? While in the US, for example, in North America, they have 60 Hertz. So when they made the standard, the NTSC standard, they chose to have a refresh rate, or the number of fields, if it's interlaced, the number of fields that being transmitted per second to be 60, while in Western Europe and in Egypt, Middle East, and so on, where the electricity has 50 Hertz, they chose to use a field rate of 50 per second. So we have 50 frames being transmitted per second. So, but have in mind that a field rate of 50 per second corresponds to 25 frames per second, right? Because if we are using interlacing, then let's say that one full frame has a width of W and a height of H. So at any time moment, you are only sending half the frame, right? W times H divided by 2. And these are transmitted, we have 50 of those per second. So it's like as if you have 25 multiplied by W times H, right? So as if you have 20 full frames per second being transmitted. You are transmitting 50, but 50 halves, okay? So, so a field rate of 50 per second corresponds actually to 25 frames per second because of the interlacing, okay? Based on this, let's look at the difference between the PAL standard and the NTSC standard. So the PAL standard is actually it's being used in the Middle East and Europe and so on. It has the frame has 625 lines, so you have per frame 625 lines. Now, out of the 625 lines, we have only 576 that represent the picture, the lines of the picture itself. The rest, the remaining of 625 minus 576, these lines, they hold some header information about the content that's being transmitted. And these are displayed at 50 fields, corresponding to 25 frames per second. That's why it's actually written as in short as 625 divided by 50. The NTSC, the ones used in the North America, the frame would be 525 lines. Only 480 of them are pictured, the rest are not, and they are displayed at 59.94 fields per second, or approximately 60 fields per second, corresponding to 30 frames per second. Okay. When video is played back on a computer monitor, it's actually not interlaced. You can imagine that if you have a video that was actually recorded according or transmitted according to the interlaced scanning, and now you're going to display it on a computer monitor. Of course, when we talk about computer monitors, there is no point actually of doing the interlacing. Again, the interlacing thing is used by TV transmission to reduce the bandwidth, reduce the amount of data that's needed to be transmitted. Why? Because you are transmitting those signals over long distances, like in the antennas, like or the satellite even. But when it comes to having a video that's actually on your computer and you're going to display it on your screen, there is no point of doing the interlacing, because you don't need bandwidth, just like no transmission is getting to happen. So in that case, we would have what's called progressive scanning. And progressive scanning is lines of each frame are written from top to bottom and directly, without like doing this odd even thing or the interlacing thing. Okay. So this is progressive scanning, is just the normal drawing at every time moment. You're drawing the whole frame, or while the interlacing is 50-50. Okay. So all of the previous, we were actually talking about the video standards, the analog one. Now let's move to the digital video standards. If we have a video and we'd like to store it and display it on a computer screen, how would we do that? So since digital video will be displayed on the same screens used for traditional video, same technology we mean, back compatibility is required. So the standard that's often used to sample video to convert it to digital form is something called the Ccir-601 Standard. So what is that? So a video frame has to be sampled in both directions. If you have a video that's coming from an analog system and or whatever analog transmission, and you're gonna convert that into digital form. So how are you going to do that? So first of all, you have to think about the size of the image. So in the vertical direction, we are going to have 576 lines for PAL and 480 lines for NTSC. We're talking here about the, like if I draw the frame here, okay, we're talking about this dimension, okay? The number of lines that we have here, if it's PAL, we have 576. If that video originally is PAL, you'll have 576. And if it's NTSC, you'll have 480. Now, how about the number of columns here? The Ccir-601, it uses actually 720 lines for horizontal sampling regardless of the scanning standard. So regardless if the scanning standard was PAL or NTSC, we will have 720 columns. So for PAL frames, you have 720 by 576. This will be 720 by 576. And the NTSC also will have 720 by 480. So this is the first thing in terms of the size of the image itself. Okay. Okay, now after knowing the size of the image, whether it's coming from PAL or NTSC standard, then next thing is how are we going to represent color in those frames that are being stored. So the Ccir-601 uses the color space called the YCBCR. This color space is different from what we covered. As I mentioned, we covered the RGB, the CMYK, the HSL, the HSB. This is another one which is called the YCBCR. So what's the YCBCR? The Y here corresponds to luminance. It's like the brightness of a pixel. So if a pixel is bright, this would be high. If it's dark, it would be low. And the CB is actually blue minus Y. It's like the value of the blue of that pixel minus the luminance value. The CR is red minus Y. So let's first think a little bit about this color space. First of all, what is that color space? It's supposed to represent all the colors. Like if you have something represented in RGB, that color space still is supposed to be able to represent the RGB in YCBCR. So the question here would be, if I have a pixel represented in YCBCR, am I losing any information about the color content of the pixel? For example, would we be able to identify the red and the green and the blue component of that pixel or not? So let's think about this. Let's assume that the Y, which represents the luminance, I'm gonna use here a very simple equation. I would assume that the luminance is the summation of the R plus the G plus the B divided by 3, like the average of the three values. Why is this a valid assumption? Because as we know, what would be a white pixel? A white pixel would have full red and full green and full blue. So if you have a pixel that is white, it's like you're adding 255 plus 255 plus 255 and dividing by 3, so you get 255, which makes sense because if it's a white pixel, then the brightness should be very high. If all are 0, it's 0. What if all of them, the RGB, they're equal to 128, which is midway like gray value, that the average would be 128. So Y is a good estimate in that case. Somehow it's not really that accurate, but still it would give you a very good estimate about the luminance of that pixel. Now, how about CB and CR? So CB is equal to B minus Y, while CR is equal to R minus Y. Now the question is, if you have YCBCR for a pixel, can you find the RGB components of that pixel or not? If you think about it, yes, it's possible. If I know the Y value, I can plug it here and here, which means I can find the blue value, okay, and from here I can find the red value. Now I have the red and the blue, I can go back to the expression of y, and given that we know y and we computed b and r, we put the r, we put the b, we can get the g. So by representing a pixel using that color space, the y, c, b, c, r, you're actually not losing anything about the color content. You still can know what's the r value, the green value, the blue value for that pixel. So it seems that this color space, okay, it's representing the same thing but in a different way. Now, if that is the case, you might be wondering, so why are we using that color space? What's the benefit of representing pixels in that standard, the one that we use for digital video for representing every frame in the video? What's the purpose of representing using YCBCR and not using RGB, the regular RGB? So let me explain this here. Okay, so the idea here is that, as you will see, that we do not represent the YCBCR for all pixels. This is what we do. In the Ccir-601 Standard, as one form of doing compression. As we said before, videos are too big, they are huge, and if we do not apply any sort of compression. So one level of compression that's being done in the Ccir-601 is to use what's called the 4:2:2 chrominance subsampling. So what does this mean? The 4:2:2 means that for every 4 pixels, the first number represents the y. So for every 4 pixels, we will have 4 luminance values. So for every pixel, you have its luminance value, its brightness. While the second number, the 2 here, this represents the blue component, which means that for every 4 pixels, we only have 2 blue values, one here and one here. And the red, for every 4 pixels, we only have 2 red values, this one and this one. So what does this mean? This means that you are storing for this pixel the 3 values, the y, the cb, the cr. While for this pixel, we're only storing y only. How about the cb, cr? They're not there. Next pixel, we're storing all y, cb, cr. Next one, only y, and so on for all pixels. So by doing this, you can imagine that if each one of the y, cb, cr takes 8 bits to store, this will be stored in 24 bits, while this one will be stored only in 8 bits. This is in 24, this is in 8, and so on. So you're saving a lot, like in this pixel you're saving 16 bits, this one you're saving 16 bits. You're saving a lot in terms of storage, okay? Now, how about the quality of the image? Now, the good thing is, and this is the whole base why this is used, that the human eye is less sensitive to variations in color than to variations in brightness. Fewer color samples are needed compared to luminance samples. So what does this mean? We as humans, we can feel little differences in brightness, but not with the same, like we can feel those little differences, but when it comes to variations in color, we cannot notice those variations that much. So what does it mean? For example, if you have a red pixel that has a value of 255, now if the 255 becomes 250, you might not notice the difference. However, if you have a pixel that has a brightness of 255 and the 255 became 250, you might actually notice that difference. So we are sensitive to variations in brightness more than variations in color. So given that information, then we are storing here color, but for this one, we're not storing the color information. Actually, we will take the color information for that position from the previous one. We can take it, just copy and paste. So no need to store it. When you are displaying the image, you just take the color information and put it here, which means that the luminance of these 2 pixels will be different, their brightness will be different, however, their color content will not. Okay? And the thing is, you wouldn't actually notice because, again, the image would be, we're talking here about what? We're saying that we have, in the PAL system, you'll have 576 rows and 720 columns. Like each pixel is very, very tiny. And by doing this, actually, you wouldn't even notice differences in quality. Okay, so the whole idea here is in the 4:2:2 chrominance subsampling, you will be able to reduce the amount of data that's being stored, and still you are not reducing the quality that much. Okay, So that is one level of compression where you're actually dropping some of the information or some of the data that we have here just for the sake of reducing the size of the video. Okay. Now the digital video, for example, as a standard, it applies 4:1:1 chrominance subsampling. So by 4:1:1 we mean that in every 4 pixels we have 4 luminance values. We have one CB value and one CR value, and actually compresses to a constant data rate of 25 megabits per second, reaching a compression ratio of 5:1. We'll talk about this later on, the idea of the data rate. The high quality DV Pro and digital S formats that are used also for digital video, they use the 4:2:2 subsampling that we talked about. Now, when it comes to also to further compression, the Mpeg standard actually defines a series of standards. There is Mpeg 2, Mpeg 4. What's the difference between these? Mpeg 2 is used on DVDs. It's actually used to create DVDs for videos. Mpeg 4 supports a range of multimedia data at bit rates from 10 kilobits per second to 300 megabits per second. So what these numbers represent is that every second of video here would be represented with 25 megabits. Here, every second of video is represented with 10 kilobits and up to 300 megabits per second. So like DVD Mpeg 4 can reach this. Mpeg 4 defines a file format. There is also the 3GP, which is a simpler version that's used in mobile phones. Next, we talk about the high definition, which we always see now in videos. So what does high definition mean? High definition represents any format that has larger frames than the standard formats. What do you mean by larger frames? So high definition videos, they use higher resolution and they may be progressively scanned. They don't need to do the interlacing thing. They would have frames with heights 720 and 1080. So these numbers are much higher than what's used actually in the PAL and the NTSC. The PAL standard uses, as we said, 576 lines, while the NTSC uses 480 lines. So now we're talking about 720 and 1080, okay? And also an aspect ratio of 16:9, these are used. So you see, like if you are, for example, watching something on YouTube, you can change the resolution of the video by switching to 1080 or 720. So what do these two numbers mean? The 720 or 1080, both numbers represent actually the number of lines that you will have in the image. So what is the aspect ratio that we say here is 16:9? This is like the ratio between the width and the height of the image. So for example, if I have an image like this, and that image here has 1080 lines, then that number here, if we call this W, we can obtain W from that ratio. For example, you will take the 16/9 and then multiply it by 1080, and that will give you the width of the image. So the high definition always uses that aspect ratio, the 16:9. Okay, and the variables are then in that case is the represents here the number of rows, whether the 720 or the 1080. The high definition frames are either progressively scanned or interlaced. If progressive scanning is used, we write the letter P. That's why actually on YouTube, for example, you would find that the video has a resolution of 1080p. What is P here? What does P here represent? P means that this is using in progressive scanning. Like at any time moment, you're getting the whole frame, not even an odd fields as we explained before. If interlacing is used, you will have the letter I written. Okay. So let's say that we have a high definition frame that is 1080 actually. Okay. So now, let's look at this picture here. If you have 1080 lines, then because you multiply this by 16/9, you will get 1920 columns. This is the aspect ratio that's fixed. This is for the high definition 1080. For high definition 720, you get 1720 multiplied by 16/9, you get 1280. The thing is, you know, like on YouTube, when you change the resolution of the video, you only use a single number like 1080, 720. Now, this number, as I said, only defines the number of rows. How about the number of columns? Why don't we specify it when we specify the resolution on YouTube, because the aspect ratio is fixed. So if I know the number of rows, I can know the number of columns directly without I don't need to specify it. For the PAL and NTSC, the story is different, because for the PAL, as we said, we have 576 lines. For the NTSC, we have 480 lines. And in both cases, in digital video, you will have 720 columns. Okay. Now, one thing that we need to talk about here, which is when you go on YouTube and, for example, let's say you have a video that's 1080, and then you reduce its resolution to 720. The difference between 1080 and 720 is now that the video would have less number of rows. Like the 720 has 720 lines compared to the original video, which is 1080. So, which means that if you're going to display that video as it is, it should be smaller because it has less number of lines. However, this doesn't happen. On YouTube, for example, if you have a container that will show the video, the size of the container does not change by changing the resolution. You always get the same size for the video. However, the resolution itself changes. So how does this happen? This is what we're talking about here. So let's say you have a video on the YouTube server that is 1080 video, stored as 1080. And you would like to display that video in 720 resolution, but in the same container as that would fit 1080 lines. Okay, so you're going to transmit, the server is going to transmit to the receiver only 720 lines, and then the receiver has to take those 720 lines and distribute them among the 1080 lines that are available in the container. So obviously each line will take multiple lines. In fact, if you divide 1080 by 720, you get the number 1.5, meaning that every line of the 720 lines should fit about 1.5 lines in that image. Of course, we don't have fractions like 1.5 lines, so let's assume, just for simplicity, that this number is not 1.5, it's like, let's say it's 2. This means every line here will be copied into 2 lines on the display. Okay, so if, let's say, these are the 720 lines, we will take one line here, and that line will be copied into 2 lines in the 1080. And we will do that for every single row that we have in the 720. And because you're copying, this is like when the image starts, like you see the video, starts looking like it's pixelized. It has a low resolution. Why? Because in that case, every line is copied into multiple lines. You can imagine if you go to, for example, 244 as a resolution, and then in that case, the one line from the 244 will be mapped into multiple lines in the 1080. That's how the resolution gets lower. Okay, so this is what this means. So we say that high definition of 1080 60i, this means that you have 1080 for the number of lines, 60 here refers to the number of fields per second, and I, if I is there, this means it's an interlaced video. If P is there, this means it's actually progressive scanning. So the whole video or the whole frame is drawn in front of you. Okay, so that's it. I'm gonna stop here. So in this lecture, we talked about, we finished the topic of color spaces, and then we moved into the topic of video and animation. We talked about video standards, digital video standards, including the Ccir-601 and the high definition, and how we actually, what high definition actually means. Okay, that's it for this lecture. In the next lecture, we're going to continue that topic. And that's it for today. All right, thank you, and I'll talk to you soon.